Okay then. Okay. So we'll start now. So we have shifted the class timings to Saturdays and Sundays from 3 to 5 p.m. Need not worry, the class material will usually last for 1 hour or 1 hour 15 minutes, and we'll keep the rest of the time for question and answers if there are any. And rest information is here. Regarding the assignments, sorry, I have not shared any new assignment now. I'll share the solution to the previous one and a new assignment in this week. So we are using these books as references. So up till now, we have been looking at things from Podzar. We'll complete the some special cases of transmission lines today from Podzar, and then we'll look at the Smith chart from DK Cheng. So I find the explanation in DK Cheng more comprehensive. So we'll use that. You can also refer to Podzar for the Smith chart as well. So Cheng has more solid examples. So we'll look at some today and maybe a couple of more examples in the coming classes. So we are here. We completed module 2 in class pre, uh, the previous class. Okay, the class before the previous class. In the previous class, we started the transmission line theory. We looked at some basic things, including the telegrapher's equations, and the wave propagation in transmission line. So we'll quickly do a revision today as well. Need not worry if you missed yesterday's class. Okay, so in the last class we started with the transmission line theory, the lumped element circuit model for transmission line, and terminated lossless transmission line. Okay, so these yeah, so some part of it was still left from the terminated lossless transmission line. So we'll cover that as well today. Okay, so we'll start with a quick recap. Also, before we started yesterday's class, we looked at two important theorems, one of them being the reciprocity theorem and the other being the image theory. So the reciprocity theorem, so we looked at the derivation. So it looks something like this, where you have this particular region, this volume, and its volume is represented by V, and the surface, total surface area is represented by the surface S, and there is this normal vector on the surface, and you have two electric sources, J1 and J2, two magnetic sources, M1 and M2, and their fields corresponding, uh, E1 and H1 for J1 and M1, and E2 and H2 for J2 and M2. And once you have this particular region, you using some vector identities, you can evaluate the volume integral to surface integral using the Gauss divergence theorem, and write this particular expression. So this is what we call the reciprocity theorem, and this particular expression takes different forms under different cases when, for example, you have J1 missing or M1 missing, or within different cases, it take different forms. So need not worry. This comes in handy sometimes, but you should know. So and we looked at three cases. So one in which the surface S had no sources, that is J1, M1, J2, M2 was zero. Where the reciprocity theorem became something like this. And then when the S was bounded as bounded a perfect conductor, in that case, the this particular surface integral vanished, and we were left only with this volume integral equals zero, and it can be evaluated something like this, where we also realize that this particular expression is similar to the reciprocity theorem that we see in the circuit theory, where if you interchange the source and the observation points, the relationship still holds. And again, if the sphere is if S is a sphere at infinity, again this particular expression is still true. Again, it forms the same relationship, but going through a different mathematics. So yeah, we looked at the reciprocity theorem, and then we looked at the image theory, where if we had a perfect electric conductor, or that is we call the ground plane, and there was source near to it, then how do we replace this particular ground plane with the fictitious source, and using this particular source we can evaluate the electric field or the magnetic field more conveniently. So yeah, this part of a single arrow is an electric source, and this double arrow is a magnetic source, and this is how the relationship holds. So this figure can help you quickly transform your problem space into a more simpler one. Then we started with the transmission line theory. So we looked at the differences between the transmission line theory and the circuit theory. One of the major thing being that transmission line theory takes into account the phase change within the circuit as compared to circuit theory, where everything consists of lumped elements and there is no phase change involved. And it all happens due to the electrical size of the element that we are looking at. So we discussed this in detail in the last class. So it's all there in the slides. You can I've kept the material as like you can go through the slides and it will give you a good idea of what if you have missed something. Otherwise, also all these things have been taken from Podzar, so you can also refer to Podzar to go through the material. And then again, we looked at what a transmission line looks like, and we took a very incremental section of transmission line such that we can again approximate the distributed transmission line into a lumped circuit. So this is what the approximation gives us. So this is an incremental section of transmission line where it has all these four lumped components: resistance per unit length, inductance per unit length, conductance per unit length, and capacitance per unit length. So all these things correspond to different properties of the transmission line. For example, the inductance correspond to the series inductance corresponds to the self inductance of the both the transmission line, and similarly resistance correspond to the finite conductivity. The capacitance corresponds to the capacitance developed due to the close proximity of the two transmission lines, these two conductors, and then the conductance corresponds to the dielectric losses in which the transmission could be. So all these correspond to different physical parameters which are involved where the transmission line is kept or how it is made. So this is what we call a two-wire transmission line. And then we looked at the telegrapher's equation. So we just performed the KVL and KCL, since we are again considering it as a lumped circuit, just because this particular delta Z is very small. So there is no phase change. And we wrote the KVL and KCL and then evaluated it using the finite difference approximation to get the differential equations. And this set of equations is what we call the telegrapher's equations. So it basically gives the relationship between the voltage and current across the transmission line in terms of RL, G, and C. Now, this particular telegrapher's equation was in time domain, and then if we had a sinusoidal steady state, we could write this particular this telegrapher's equation in frequency domain, and this is how it looks. So this particular form is more popular among microwave engineers, and also very important if this could be asked in your exams. How do you go around deriving the sinusoidal steady state telegrapher's equation for a two-wire transmission line? Now, once we had this particular the telegrapher's equation, so now we can use. So they are very similar to the Maxwell's equation that we have, and now we can use this to write the wave equation, following all the steps that we have already looked at by developing the wave equation from the Maxwell's equation. And over here, this gamma term is the propagation constant, and it is a complex number, and it can be expressed in terms of R, L, G, and C using this expression. So this is what you get. So a very important expression will help you solve a lot of questions. Then we had the wave equations, and its solution again is can be given using is given over here, and we have seen how this is derived in again Maxwell in the wave propagation using the Maxwell's equation, where we had the electric field and the magnetic field. So the same thing, where minus gamma z e power minus gamma z is a term representing the wave propagating in the forward direction, and e power gamma z represents the wave propagating in the negative direction. So this is the solution, and using the the telegrapher's equation for voltage and the solution for the voltage from the wave equation, we can we can write the expression for current, and then comparing the two current expressions, one over here and one over here. So if you compare this, you can we can define this particular term known as the characteristics impedance, which is given by r plus j omega L by gamma, and substituting the value of gamma over here, we can write this as r plus j omega L divided by g plus j omega c whole under root. So this is called the characteristics impedance, and this is a very important term. Will be used very frequently in the coming lectures, and if you are working with antennas or microwave circuits. So yeah, very important term. Now, once we had defined the characteristics impedance, and now we can give the expression for voltage and this incident and voltage and current, and reflected voltage and current in terms of the characteristics impedance. So this and using this particular Z naught, we can again write the expression for the current in the transmission line in terms of the incident voltage and the reflected voltage. And again, we define the wavelength and the phase velocity on the transmission line. So very analogous to electric field and magnetic field formulation. So is going on over here. So you can relate it directly. So if you have gone through your electromagnetic course properly, you will be able to see the expressions and see the similarity and solve the problems. Now, then look. So up till now, what we were looking at was this particular set was a generalized two-conductor transmission line, and it included losses. So the R and G terms are basically due to the finite conductivity of the two conductors in the transmission line, and G is due to the dielectric losses. So if our system was to be lossless, the R and G terms will vanish and will only be left with L and C. So setting R and G equal to 0, the complex propagation constant will simplify, and what will end up is with attenuation constant alpha equals 0, and we will only have beta equals omega root LC. And so yeah, so your gamma will only be equal to j beta, and you can again simplify your telegrapher's equation and your solution to wave equation using by replacing gamma by j beta. And similarly, your characteristics impedance will again simplify to only root under L by C. So this becomes very simple. And and why we are doing this is because in most cases the losses are very small, and going about the equations with the complex numbers is tedious. And if you consider it to be lossless transmission line, and you know that your material you're using is has very low loss, you can simply use these expressions, and just and the deviation from the measured results, and the ideal lossless condition won't be too much. Now, we had so use so in the up till now we derived the expression for current in terms of for incident and reflected voltages, and again we have the voltage in terms of incident and reflected voltages, and we have this Z naught equals the characteristics impedance. Now, so this is the set of the solution that we have right now. And now, if so up till now, what we're considering was that this transmission line, we were considering this as a small section of transmission line. Now, what if now looking at a more general idea is that this transmission line will probably start somewhere and end somewhere. So, looking at the end of the transmission line, where we are terminating with this particular ZL a load. So, if we include this into the R circuit, now we'll have to solve some more equations. Now, this particular ZL and this particular this load is at Z equals to 0. Now, putting Z equal to 0 in these two expressions, we will and we can equate it to ZL. So this is what we'll end up with, and we can now write the reflected voltage in terms of the incident voltage, the load impedance, and the characteristics impedance. And using this, we'll solve. We'll use this. And looking at now, we define a term called the voltage reflection coefficient. Now, this which we represent it using gamma, the capital gamma, which is the ratio of the reflected voltage by the incident voltage. And now using substituting the value of V naught minus from over here, we get that the reflection coefficient is equal to ZL minus Z naught by ZL plus Z naught. So again, this is a very important relationship. So now we have defined the voltage reflection coefficient, and now we'll use this voltage reflection coefficient and again substitute it back into the solution for the voltage and current from the wave equation. And now we can express the voltage and current in terms of only the incident voltage, the reflection coefficient, the propagation constant, and the characteristics impedance. Now we already have got the solution in a very acceptable form, and we try to find out the average power inside the transmission line, and now this average power is given by half of real part of Vz Iz conjugate. Now substituting the values of Vz and Iz and taking the conjugate and evaluating it, we get something like this, where we need to take only the real part of the term in the braces. And these two terms, the gamma conjugate and gamma terms, they are of the form A minus A conjugate, and this evaluates to be only to be a totally imaginary number. So we can ignore this, and taking the real part, we get 1 minus gamma square. So yeah, we take that, and this is how the power looks like. So we can see that this is actually representing the incident voltage. If you multiply this term as with 1, and if you multiply gamma with V naught, is actually the reflected voltage. So the average power is basically the incident power minus the reflected power. So using that, and then we defined the what we popularly use the term we call the return loss, which is actually the minus 20 log of gamma over here. So this is very commonly used in a lot of while you are designing a lot of microwave devices or antennas. So you calculate the return loss. So we defined that, and then again we defined the voltage across the transmission line, and this is the expression for the voltage in terms of the reflection coefficient, and so we're generalizing the expression for voltage across the transmission line. And if you look closely, you see that the voltage is varying across the transmission line, and the power is actually constant. So this gives us the idea that the impedance throughout the transmission line must be varying, and using that we'll come to some more conclusions. And again we can find out the maximum voltage and the minimum voltage from this particular expression by substituting the exponential term equal to 1 or minus 1. So under different circumstances you can find out the maximum and minimum voltage, and we also define the ratio of this maximum voltage and minimum voltage as the standing wave ratio or the voltage standing wave ratio. Yeah, so and again substituting the values, we get the standing wave ratio as 1 plus mod of gamma divided by 1 minus mod of gamma. I see there is a question. Does the imaginary part in the previous equation indicate that a portion of the incident power is absorbed back? Okay, the imaginary part in the previous equation. Let me see. Okay, so usually the imaginary part is usually known to be non-propagating is what I can recall with antennas. So it's usually yeah. So it means it usually, so the imaginary part of anything is usually what is being lost. So yeah. So this particular thing means it is being absorbed back. Yes. So I believe your conclusion is correct. Uh, Yeah, so this thing it is being absorbed back, and the only thing we are looking at is the real part of the power, which is actually propagating through the transmission line. Now, so we define the voltage standing wave ratio, again an important term that will come into play, especially when since we are looking at Smith chart today. And now, yes, so and then we also defined the generalized reflection coefficient from the previous expressions, where we took the voltage of the incident voltage, the reflected voltage and the incident voltage, and this particular term turned out to be gamma at position 0 and e power minus 2 j beta l. So yeah, so all these expressions we derived in the previous class. Just in case if you missed yesterday's class, I have shared the class recording in the WhatsApp group. I hope everybody is added in the WhatsApp group. If you are not, please let me know. Yeah, we looked at all these expressions here in the previous class again, and then again we defined this a very important term called the input impedance. And input impedance is what, if you are trying to look at the transmission line at certain point, what impedance is what you see. So so for example, let me use a pen over here. So example, if you are looking at the transmission line from this particular point, what is the impedance that you see at this particular point? So this will actually be, so for this, the impedance that will come into play will be the characteristics impedance of the transmission line and how this particular transmission line is terminated. So these two things will come into play. And so at this particular point, if you're trying to find out the input impedance, what you can do is take the ratio of the voltage at this point, and the ratio of voltage and the current. And now we already have the expression for voltage and current that we derive from the we derived throughout the previous slides, starting from the results for the solution for the wave equation, and then substituted the characteristic impedance and the reflection coefficient. Using that, we substitute the values, and then we get this particular expression. So this expression is important, and then we will evaluate this now. So we derived the expression for input impedance like this, and now we substitute the reflection coefficient that we derived in one of the previous slides back into this expression. And after evaluation is what something that we get over here. So this is the very popular form of the expression for input impedance, and very frequently used in the gate exams and other competitive exams. So make sure you remember this. So this expression you'll have to remember, and we call this as transmission line impedance equation. So we went through a lot of maths in the previous class to derive all these expressions, this important expression. And now we'll start today with some things that we could not cover in the previous class, and we'll start with Smith chart today. So what if this transmission line, the termination, this load impedance was a short circuit? So we have already derived the generalized expression for the load impedances, and now what all we do is we substitute ZL equal to 0, and doing that we get the reflection coefficient equals -1, and this implies that the standing wave ratio will become infinite. So the standing ratio comes out to be infinite, and the we can define the again the voltage and current on the transmission line by this expression. So we are doing is using the trigonometric formulas and evaluating this. So this is the expression for voltage, and this is the expression for current. And now we can also define the input impedance by substituting this ZL equals 0, and this will turn out to be Zn equals J Z naught tan beta L. So we can see that this has the input impedance is purely imaginary, and for any length that we take, it will oscillate between the plus infinity to minus infinity. So we'll plot these expressions now. So there's a question. This J tan beta L is same as the tan H beta L. Yeah. So tan H beta L under the assumption that uh, when we write tan H beta L we write as gamma L. So if gamma is imaginary, then this tan H terms converts to J tan. So right now we're considering that this particular transmission line is lossless. But yes, in case of lossless, these are equivalent. Yeah. Okay. So looking at the plots for the voltage, current, and the impedance for short circuited transmission line. Tan H beta L. I'm not sure, like I'm following it correctly. It should when you write tan H, it should be J beta L, and again, I'll have to look into this, but yeah, it should be tan H J beta L, which evaluates to J tan beta L. Yes, tan H gamma L. And in case of lossless, this gamma will become J beta, and then this tan H can be evaluated to J tan. Is it a unit step function? I believe, I'm not sure. I can't recall the plot for tan H right now, and especially for complex input. I'll have to plot and see. Maybe I'll deliberate on this in the next class. But this particular thing, when if you have a lossless case, we'll look at the plot right now, where it will evaluate to J tan beta. So we'll look at that right now, and maybe I'll look into this your question in the next class. So one important thing that we notice is that the impedance is periodic in L. So we already have the express. Okay, so we'll let me put all of them together. So we already have seen that this input impedance is written in terms of tan beta L, and we know that this tan function is periodic, and it is periodic in the multiples of lambda by 2. And this is how it goes. So the voltage is varying as the sine, and this current is varying as cosine, and this input impedance is starts from 0 and then goes to infinity, and then again in the comes from minus infinity to again 0, and then again goes back to infinity. So this is how, if you move along the transmission line, this is how the impedance plot will look like. Now, doing a similar treatment for ZL equals to infinite. So what if this ZL was to be open circuited? So again, we'll put the value of ZL equal to infinite in this expression. And since you cannot directly put it, what we'll do is we'll multiply and divide by ZL and write this thing as 1 minus Z naught by ZL, and then take the limit. So you know the steps. We'll substitute the value of ZL under the limits, and it again we'll find that this reflection coefficient turns out to be equal to 1, and even either 1 or minus 1, the standing wave ratio will turn out to be infinite. So again, it is infinite, and uh, substituting the values again in the both for voltage and current, we get these expressions. And similarly for the input impedance, this will change from tan to cot. So again, this is purely imaginary, and for any value of L, and this will again have the periodicity of lambda by 2. Again, plotting them. So this plot again is periodic in lambda by 2, and the plot only slightly changes, but again you can see it will vary from minus infinity to come to 0, and then again go to infinity, and this trend continues. So this is how the input impedance plot will look like if you make the transmission line open circuited. And okay, maybe I'll pause some time for you to grasp this thing. So we covered uh, quite a lot from previous class, and we looked at the case of short-circuited and open-circuit transmission line. So all this is an extension of what we already did in the previous class, where we had a load impedance attached to the transmission line, which is substituting the value of Z0 and ZL. And now we'll substitute lambda by 2 and lambda by 4 to see what results come in that cases. So yeah, maybe I'll pause over here, take questions if you have regarding what we covered now. Uh, Else we'll move forward. So maybe I'll take a pause over here for you to grasp the things. Okay. So I hope that was sufficient time since we already started late. Maybe we can continue and so we'll have short breaks and then take any questions at the end if we have some time, or we can take the questions in the next class. So yeah, what if this L were to become lambda by 2? So we'll just substitute this L equal to lambda by 2 over here. We know the beta is 2 pi by, again, lambda, and substituting that will end up with this. Let me calculate. Yeah. So yeah, so we'll have this as pi, I believe, and then using that will only so tan pi, I believe, is 0, right? Yeah, so tan pi is 0, and this will turn out to be Zn equals to ZL. So a very interesting observation. So if for at lambda by 2 distance, this Zn will be the effect of the transmission line vanishes, and we only see the load impedance. Now, yeah, so again, the inverts, the a half wavelength line or any multiple of lambda by 2 does not alter or transform the load impedance, and regardless of its characteristic impedance. So you can see Z naught from this expression vanishes in case of L equal to lambda by 2. So whatever, for example, if you have a transmission line and you're looking at it from this particular point, and this particular transmission line has some characteristics impedance as Z naught, and you have some load attached over here, and this is ZL. So whatever this Z naught may be, if this particular length, okay, this become very clumsy. So whatever this length may be, if this, so okay, sorry. So whatever this particular Z naught may be, if you have this particular length as lambda by 2, it won't matter. So you will only see ZL. And what if it will be to become lambda by 4 or any multiple of lambda by 4? So this particular expression will reduce to something like this, Z naught square by ZL. And we popularly use this in for impedance matching, and we call this as quarter wave transformer. So a special case arises when you write when you can calculate this particular Z naught uh, okay, equals uh, root under Z in, okay, I don't know, there is some lag happening. So Z in and 2 ZL. So you get the idea, I believe. Z in into ZL. Yeah, this is taking forever. Okay, so basically, if you evaluate and take the Z naught into the left hand side and write in terms of Z in and ZL, you'll get some expression, and then you can use this expression to match an input impedance of Z in and a load impedance of ZL using this particular quarter wave transformer by calculating the Z naught. So this will come in handy in future classes, and if you're working with microwave circuits. Now, so another case arises when a transmission line of certain characteristic impedance Z naught is fed to another transmission line with characteristic impedance Z1. So, and if you take a case where this particular transmission line is very long and So if it is infinitely long, or if it is terminated in Z1 itself, so what will be the what will happen at this particular interface when this particular Z naught and this transmission line ends up to Z1. So if this is matched in terminated load, or it is infinitely long, so it will this particular so we have a chain, will have an impedance mismatch over here, and we'll look into the mathematics involved in this. So we'll have some so all so the way the incident wave, some of it will be transmitted and some of it will be reflected. Now the reflection coefficient is now given as Z1 minus Z0 by Z1 plus Z0. So what we have done is we have replaced the ZL by Z1. So for this particular transmission line, we're looking at this particular transmission line as uh, the load impedance. Yeah, sorry about this scribbling. But yeah, you get the idea. So we have found out the expression for reflection coefficient if a transmission line is terminated in another transmission line, and and since not all of the wave is reflected, some of it will be transmitted. So we need to find out the transmission coefficient. So the voltage for at this particular region where Z less than 0 is given by this expression, where we have the incident wave and then the reflected wave as incident wave into the reflection coefficient. And for wave in this particular region, Z greater than 0, we can write the expression for the voltage as the incident magnitude into the transmission coefficient, and wave is propagating in this direction. Now, since if we evaluate at this junction, since, following uh, the expression for voltages, we get that the reflect this transmission coefficient should be 1 plus reflection coefficient, and then substituting the values, we find out the transmission coefficient as 2Z1 by Z1 plus Z0. So yeah, this might look contradictory, but this reflection coefficient itself is carrying the positive or negative symbol within it. So need not worry that this should be minus symbol over here. And again, we had already defined the term return loss, and now whatever the wave is being transmitted over here, we so whatever the wave is transmitted, so we refer to we define this particular term as called the insertion loss, which is basically the 20 log of transmission coefficient. So this is another important term. When while designing a device, we calculate the return loss and the insertion loss, and we characterize the device using these two terms. So this is how you calculate the insertion loss. So yeah, so that was all that we were to cover today from the transmission line part, from the special cases of transmission line. And now we'll start a new topic called the Smith chart. So maybe I'll again pause over here and let all this sink in. So before we start with a new topic. And meanwhile, if you have any questions, you can write them in chat, or we can take questions whenever you like. So, any questions from till now from the whatever we covered? I've started the recording, right? Yes. Okay. So, I believe everything right that we covered till now was only the special cases of what happens if ZL is something, or what happens if the length is something. So they were all special cases of the mathematics that we derived in the previous class. Now we'll start with a very important topic especially if you are looking at towards giving an exam on microwave theory. So the Smith chart very popular among faculties. They ask it very frequently in the exams, and as it turns out, it becomes really tough while attempting the questions. So yeah, it sometimes is also confusing. So we'll go through the step by step how the Smith chart was designed, and then look at some questions. So we'll look at some simple questions today. Yeah, this figure looks very complicated and very daunting. So this Smith chart, this shown in the right side. Let me change my pointer. So this particular Smith chart, this is shown over here, is a graphical aid. Basically, what we use this is for to avoid going through complex mathematical equations, and we try to solve the problem graphically. And this was developed by Philip H. Smith. So Philip was working in Laboratories during where he developed this Smith chart. And as written over here, it at the first glance it may seem intimidating, but key to understanding this is that it is a polar plot of the voltage reflection coefficient. So all these circles are corresponding to something, like we'll have some constant R circle, constant circle. So these are basically circles for different values. So that is how this chart is made. Uh, but yeah, this only helps you in guiding where to plot the point and start with your problem. But yeah, don't be afraid of this. We will look into this in the coming slides. So, but before we start with the Smith chart, what we'll do is we'll look at the Smith chart in the Cartesian coordinate, and then we'll go towards the polar coordinate, because the Cartesian coordinate will help you understand the how the Smith chart is designed. Going directly to the polar coordinate will probably complex things. And yeah, for this, the coming slides are prepared from David K. Cheng and not Pozar. So the material you will be seeing now will be from Cheng, and you can refer to the textbook if you apart from the slide if you need some help. Also, Pozar also has some pages on again Smith chart, but I find the text in Cheng to be more like easier to understand. So to understand the Smith chart, for a lossless transmission line. So again, we are considering the transmission line to be lossless. We'll have to examine the voltage reflection coefficient of the load impedance. So again, so we have already derived this particular relationship, and now we can again, since we know that this reflection coefficient is might be complex, so we again use we can define this in terms of the polar form or the Euler form. So again, there's a change of notation. We are using R naught because we're considering the transmission line to be lossless, and in case of when the transmission line is lossless, the characteristics impedance is real. So yeah, using that, so we have defined the voltage reflection coefficient, and again, the load impedance is again ZL, and what we are doing is what we will normalize everything with respect to the characteristics impedance. So again, so this is root under L by C. Make sure you note that earlier we were referring to it by Z naught. Now we will be using R naught. And when you normalize, what you do is you normalize the real part and the imaginary part, and now we can write this as R plus JX. And this after normalizing, this particular term becomes dimensionless. So the R is the normalized resistance and X is the normalized reactance. So remember this. And now what we do is we substitute this particular expression back into from where we started, and we end up with this particular expression for the reflection coefficient. Now, the reflection coefficient can also be written in terms of A plus JB form, and and also which is equal to ZL minus 1 by ZL plus 1. So since this is dimensionless, so we don't have any issue over here. Now this this gamma r and gamma I are the real and imaginary parts of the voltage reflection coefficient. Okay, so yeah, up till now, what we have done is we started with the reflection coefficient, wrote it in the polar form. We had this particular expression over here. We normalized the load impedance, substituted it back into this expression over here, and this is what we have got till now. Now, we can also write the inverse relationship where we express the normalized load impedance in terms of the reflection coefficient is given over here, and then we can also replace this term by the magnitude and the phase term of the reflection coefficient. So we can rewrite it like this, or we can rewrite it in this, where we have the real and imaginary part of the normalized load impedance represented in terms of the real and imaginary part of the reflection coefficient. So this was in the polar form or the Euler form, and now this is again we are writing it in the x plus jy or a plus jb form. So now we'll be using the second expression. Okay, so we started with these two expressions, wrote the reflection coefficient, and then wrote again the load impedance in terms of the reflection coefficient. And now we'll stress on this particular equation. Now what we can do is we multiply both the numerator and denominator of this particular expression by the complex conjugate of the denominator to separate the real and imaginary part. So this is a very simple step of mathematics, but will yield very useful results. So using that, we have now separated the real. We have found out the r and x from this expression. So all we did was that we multiplied the denominator with its complex conjugate to get the real part and imaginary part separate. So maybe I'll pause over here, let you look at the expressions. So how we went about from the expression for reflection coefficient, normalized the load impedance, found out the reflection coefficient in terms of the load impedance, then again found out the load impedance in terms of the reflection coefficient, separated the real and imaginary part of the normalized load impedance. So this is what you have done till now. So I'll let you look at the expressions now. Yeah. Maybe I can take questions also now if you have any about what we have done till now. Any step if you could not follow, you can ask. Okay, so I guess that was enough time for you to look at the expressions. So need not stress. All these thing is being done so that we can understand how the Smith chart was designed. All these things you might be asked in your exams to derive these expressions, but yeah, won't you don't really need to stress to remember all these steps. You just should be able to grasp how we are going about the derivation. So our aim was to separate the real part and imaginary part of the normalized impedance and express them in terms of the real and imaginary part of the reflection coefficient. Since we, as you stated in the beginning, that Smith chart is basically the circles of the reflection coefficient. So that is how we are trying to express. So so now we'll take the real part of the normalized load impedance and start with the evaluation. So what we'll do is we will try to plot the locus of R, and this particular locus of R, for that we'll rearrange this term, and it can be rearranged to form some this particular expression. Now, if you look closely, this expression is the equation for a circle, where you have where if you have your coordinates as gamma r and gamma I. So the r by 1 plus r term is basically a shift in the coordinate, a shift in the center of the circle, and 1 by 1 plus r is the radius of the circle. So we can write this particular locus in this particular form. And again, so what we have done till now is we started with these two expressions, found out the reflection coefficient. Again, we wrote down the impedance, and again try to separate the real and imaginary part. And now we are looking at this particular real part, and this particular real part we are trying to plot the locus of r. And as it turns out, this can be plotted like a in terms of circles. So yeah, as we stated, the radius of the circle is 1 by r, and it is centered at r by 1 plus r and 0. So, and if you change the values of this r, you will get different circles. So the radii will change, and if the center will also change, and you'll be able to plot a number of circles. So we'll do that now. So if you can look okay, so no need to focus on all the lines. If you just focus on the solid lines, okay, the solid circles. So as you can see, this for different values of r. For example, this particular circle is for r equal to 0, the biggest one. Then r equal to 0.5 will give you this particular circle. R equal to 1 will give you this circle. R equal to 2 will give you this circle. And if you keep increasing, the circles will become smaller and smaller. And if you as you can look over here, the coordinates are gamma I and gamma r. So you'll have to only focus on the solid circles. So this is how the locus varies for different values of r. And yeah, so for different if you vary the value of r, you will get a family of circles. So, and all of them will somehow will pass through this particular point. So we'll look at the important points in the next slide. And what another important thing that we're considering right now is that we're only considering the values for gamma less than 1. And for gamma greater than 1, this particular which so will be a circle which will lie outside this. But again, gamma greater than 1 means nothing. It means that the reflected wave has a magnitude greater than the incident wave. So that makes no sense. So we will disregard everything outside the gamma equal to 1 circle. Now, let's look at the salient properties of the R circles, and then we'll take a pause. So the important things, all these R circles lie on the gamma R axis. So this is the gamma R axis, and all these circles, the solid circles, if you take a look, so all these circles, its center will lie on this particular line. So maybe I'll use a pointer over here. For example, this particular this circle has its center somewhere over here, and this bigger circle will have its center somewhere over here, and then the even bigger circle will have center somewhere here, and the biggest circle has a center at the origin over here. So all the center of all these circles are lying on gamma r axis. Now, the r equal to 0 circle having a unity radius and is centered at the origin is the largest. So, since we are considering only plots where mod of gamma is greater than 0, less than 0. Sorry, less than 1. So this is the largest circle, and its center is at the origin, and it is the largest circle, and its radius is equal to 1. Now, again, the R circles become progressively smaller, as you can notice. For for example, for R equal to 0, this is the largest circle. And now R equal to 0.5, this becomes smaller. R equal to becomes even smaller. R equal to becomes even smaller. And for R equal to infinite, will be just this particular point over here. And yeah, so it increases from 0 towards infinite, ending at gamma r equal to 1 and gamma I equal to 0. So gamma r equal to 1 is this line, gamma r equal to 1, and gamma I equal to 0 is this line. So it will end over here. So yeah, and again, for all R circles, they will pass through gamma R equal to 1 and gamma I equal to 0. So all the circles will pass through this point over here. So these are the salient properties of the R circles. So we were looking at the R circles, and in the next slide in the next coming slides we'll look at the X circles. So I'll pause over here and let you look at the chart and the salient properties. So and if you have any questions, maybe we can discuss now. Also, you have to note that all these things have been plotted and found and observed from only this expression, just this expression, and which came from only expressing the the normalized real part of the load impedance. So all we are looking at is the real part of something wrong with the pointer. Okay. So we are looking at the real part of normalized load impedance, which is R, and we try to express R in terms of the reflection coefficient. So we'll look at the second expression. We started with these two expressions, then express the reflection coefficient in the terms of load impedance, then the load impedance in terms of the reflection coefficient back again, uh, wrote it in the polar form, then express the polar form in terms of the Cartesian form, uh, separated took this expression and separated the real and the imaginary part. Um, and in the previous case, we looked at this expression, and now we look at this the imaginary part of the reactance part of the load impedance. Now this plot using this expression, we try to find out the locus of X. We'll end up with the next this expression looking like this. Now again, this is again also equation depicting a circle where the radius is 1 by x, and the center lies at 1 and 1 by x. Sorry. So the center lies at f1 comma 1 by x. So again, so written text over here. The radius is 1 by x, 1 by mod x, and the center is at gamma r equal to 1 and gamma I equal to 1 by x. And again, different values of x will yield different circles. So you'll get a family of circles corresponding to different values of x. So we'll do that again. And right now, you need to only focus on the dashed lines. So the dashed lines are a part the arcs or the arcs of the circles. So they're not completed over here, since we're just looking everything inside this big one, this one big circle. And so we're looking at everything inside gamma equal to 1, and which is this big circle, and with inside that or you'll have these particular circles. So for example, x equal to 2 will plot something like this, x equal to 1 will plot something like this, x equal to 0.5 will be a line like this, and x equal to 0 will actually become the a gamma r equal to 1 line. So this will actually become the axis it is actually a a circle with infinite radius, as it turns out. So it will become a straight line over here. And again, if you start decreasing the values, x equal to 0.5 will you'll get the symmetric plot. So all these circles will have their centers on this axis, and the radius the radii are varying. So only focus on the dashed circles over here. Now looking at the salient properties of the X circles, so all these, the center of all these circles will lie on the gamma r equal to 1 line, which is this particular line. Maybe again, I'll try to use the pointer if that works. So everything will lie on this line, this particular line, all these centers. And for X equal to 0, the for inductive reactance, they will lie above the gamma I equal to 1 line. So so all the for X greater than 0, everything will lie, the centers will lie on the positive side. And for X less than 0, all the centers will lie, all the circles will lie below this particular line. And now the for X equal to 0, the circum becomes the gamma r axis, as I already stated. So for X equal to 0, you get this particular line, this axis. Now the X circles becomes progressively smaller as mod X increases from 0 to infinite. So as you so for X equal to 0, you get a circle with infinite radius, and for X equal to infinite, the circles become progressively smaller. For example, this will become small like this, again smaller like this, and then it will, for X equal to infinite, you'll just get this particular point over here. Similarly, the same thing happening on the top side as well. So, and again, all these X circles pass through this point, gamma r equal to 1, gamma I equal to 0 point. So this particular point over here, all these circles will pass through this point. So I'll again pause over here, let you look at the salient features and the plot. So you need to focus only on these dashed plot over here. I'm sorry for not putting up a better image, but again, this image is also present in DK Chang. Maybe you can refer to the textbook with more detailed information. Okay, so we have got time. So maybe in a couple of more slides, we'll look at some more information on this Smith chart and a couple of questions. Okay, then we'll proceed. So looking at all the things together, so we had derived the locus for R and locus for X. So these are the two expressions that were involved in designing this particular chart over here, where the solid lines are the R circles and the dashed lines are the X circles. And so we'll look at some important points, whatever we have concluded. A Smith chart is a chart of R and X circles in the gamma R and gamma I plane. So so the coordinate systems are gamma I and gamma R, and this particular the plot is what we call the Smith chart. And again, this is an important consideration, that the reflection coefficient must everything that is being considered is considering this mod of gamma is less than 1. And again, also this can be proved that the R and X circles are everywhere orthogonal to each other. So if you take any point, for example, over here, any point over here, or a point over here. So at all these points, wherever the R circles and the X circles intersect, they will be orthogonal to one another. The intersection of R circle and X circles define a point that represents a normalized load impedance ZL. So again, so after designing all these things, we're coming back to the relationships that we'll be using to solve the problems. So at any point that you take, for example, if you take let's take okay, so there is one point already over here, this particular point P over here. So if you take this particular point, so what you can do is you'll have a X circle like something like this going about. You'll have an, and you will also have a you'll have also have a R circle something like this. So for any point you can find out the R circle and the X circle, and if you find out if you find out these circles, you'll get the value of R and X. And what you can do is you can write that point as ZL equals to R plus JX, and this particular point will gives you the normalized load impedance on the Smith chart. And to find out the load impedance, all you need to do is multiply the this normalized load impedance with the characteristics impedance of the transmission line that you're considering, and you'll get the load impedance. Yes. So the load impedance can be just found out by multiplying the characteristics impedance into the normalized load impedance from the Smith chart, as if you take any point, and you'll get the this actual load impedance. And since Smith chart plots everything in the normalized form, it can be used for calculation concerning lossless transmission line with arbitrary characteristic impedance. So you'll see in the examples that we'll do today that since everything is normalized over here, the same chart can be used to solve a problem concerning a transmission line with 50 ohm impedance or 100 ohm impedance. Since all the points are normalized on this particular Smith chart. So these are the essential points that we have regarding the Smith chart. So up till now, we have seen how a Smith chart is made, and in coming slides will solve some problems as well. Okay. So some more important points. For example, if you take this particular point P, in the previous slide that we tried to draw the this particular R circle and the X circle, right? So this is the X circle concerning like this. So if you look closely, this particular circle is corresponding to X equal to 0.5, and similarly, if you make the circle, this will come out to be X equal to 0.6. So for this particular point, this X will come out to be 0.6, and similarly, if you try to draw this particular R circle, this will come out to be, for example, this particular circle is R equal to 2. So this will come out to be somewhere less than 2 because this one is R equal to 1. So this will come out to be somewhere between 1 to 2. And as it seems, it comes out to be 1.7. So for this particular point P, we have R equal to 0.7 and X equal to 0.6, and hence we can write the ZL equal to 1.7 plus J 0.6. And now, similarly, if you look at this particular important point over here, this is as PSC, where gamma R is equal to -1 and gamma I is equal to 0. So this particular point represents a short circuit because as you know, the reflection coefficient becomes -1 when you have a short circuit, and similarly, if you have an open circuit, the reflection coefficient will become 1. So this particular this point over here refers to an open circuit. So these are the two important points that that concerns us in the Smith chart, and then now we have also seen how to locate a point. If, for example, if we had some load impedance given as uh, alpha plus, okay, no, maybe not alpha, maybe if we have something written in form of P plus J Q, then we can normalize this particular point, and then we can find out the R circle and the X circle and like plot it over here. So we know how to plot a point on Smith chart now, and we know the important points PSC and POC, and this okay. So Smith chart in this figure is marked with gamma R and gamma I rectangular coordinates. And again, yeah, as in the beginning we were saying that The same chart can be marked with the polar coordinates such that every point in the gamma plane is specified by the magnitude and the phase angle gamma t. So this particular chart concerns in the rectangular coordinate systems, and now this particular plot can also be modeled in the polar in polar coordinate system, and that is the Smith chart that we that is commercially available and or that we frequently use. So if so drawing this same Smith chart in polar coordinates will look something like this, where we have this PM and where we have the short circuit and the open circuit points over here. So we'll look at these points now. So Smith chart, okay, so we already read this, that same Smith chart can be modeled with polar coordinate system, and this is how that looks like. Now, and this is illustrated in this particular figure, where the several gamma circles are shown in the dashed lines. So in the previous chart, we did not have the gamma lines drawn, but so now we also will draw the gamma lines as well. So this dotted lines, if you can see this particular line circle and this particular line. So in this particular circle, all they correspond to the gamma circles, and you can see that this gamma equal to 1 is the outermost circle over here. And as you increase, as you decrease the value of gamma, this particular circle becomes shorter and shorter. And as we read in the previous slides, that we are only concerned for everything lying inside the gamma equal to 1 circle. Everything outside is not into the consideration. Now, the gamma circles are normally not shown on the commercially available Smith chart. So this is very important to note, that the Smith charts that you will buy from a shop or you find it online, so they won't have the gamma circles already drawn. But once you have located your this particular load impedance, normalized load impedance, you can simply use a compass to find out that particular point and draw the circle. For example, if we wanted to draw the gamma circle for this particular load impedance, some load impedance. So we'll just find out this particular point P over here, and then we'll take the radius from origin to this particular point P, and then just draw this particular this circle over here. So no need to worry for the gamma circles. And this is how the Smith chart in polar coordinate looks like. So we looked at the Smith chart in the rectangular coordinates. We looked at the Smith chart in polar coordinates. Now, an important thing to notice is why this Smith chart is useful. All these things will come now. For example, the fractional distance from the center to the point. For example, the center is this particular origin over here, and the point we are considering this. For example, this P point we are considering. The distance between these 2 points, is actually equal to mod of gamma. This particular distance is equal to the mod of gamma. So if you have some particular point as load impedance, you normalize it, plot it in this Smith chart, and just find out the distance between the origin and that particular point, and the distance will give you the reflection coefficient and the load reflection coefficient. So it's that easy. You don't need to calculate anything except that you'll have to normalize the load impedance that you know. And the angle that line may to the point is the real axis is the phase of the reflection coefficient. For example, so all you need to do is you just extend this particular line over here wherever this particular cuts, and you find out with the real axis. So this is your real axis. So if you calculate this, if you find out this angle over here, this will give you the phase as well. So you can find out the magnitude of the reflection coefficient and the phase of the reflection coefficient, and hence you have already defined the reflection coefficient. So the graphical determination circumvents everything, the calculation using this particular expression over here. So, for example, if you wanted to calculate the reflection coefficient, then you'll have to uh, then you will take your ZL, normalize it, subtract it one by one, add one to it, and take this particular fraction, and then you will get the reflection coefficient. All this can be circumvented by just plotting this particular point over here, just measuring this line, and then extending this line and measuring this angle. So this becomes fairly simple if you're looking at calculating the load reflection coefficient for a particular load impedance on a transmission line. So I'll again pause over here. Maybe if you have any questions. Okay, so we'll proceed. So some important observations, for example, if as we saw, if we take this particular point P and we draw the gamma circle, what will happen is that it will intersect this the real axis on 2 points. So one will lie on the right hand side of the origin and the other on the left hand side of the origin. So this, which we denote it by P capital M and P small m. Now these 2 points have some significance. So let me post everything here. So for x equal to 0, so for this particular point, you have some value of this r and this jx, right? So what you do when you move along this particular circle, you're keeping your yeah. So if you so if you can maintain this particular radius, what you are doing is then you're making x equal to 0, and what will happen is you'll reach these 2 points. So what will happen is on this particular line, everything that you mentioned is purely resistive. Yeah. So so on this point, if on this line, if you are moving, so your x is equals to 0, and hence this means your load impedance is purely resistive. Now, for RL greater than R naught, we have will ha at PM we'll have RL greater than R naught. So yeah, so at this particular point, if the load impedance will be greater than your the characteristic impedance, and hence you will get your R greater than 0. Just a second. Yeah, so if you can see that this R is equal to 1 is this particular circle, R equal to 2 is this circle, and as soon as you cross this origin point, your R will become less than 1. And that goes on from this. So as soon as you move away from the origin on the left hand side, the R value becomes less than 1. So, and on the right hand side, the R value will be greater than 1, and this implies that RL will be greater than R naught. And similarly, if you are lying on the left hand side of the origin, so you will have R less than 1, and and similarly for PM you will have RL less than R naught. So these are some observations considering where you are on the R circle, like on the real axis, and considering the value of X and R. And an important thing is that the standing ratio for RL greater than R naught is defined as RL by R naught, and this particular relationship helps us establish that since if like for example, if you plot this particular point, and then you can and then you go moving on this particular circle, if you get this PM, and if you have found out this the value of PM, you can directly say that this PM is the voltage standing wave ratio, and you don't even need to use this particular relationship. So, so if you want to calculate the standing wave ratio, all you need to do is plot this particular point, draw a circle, and wherever this cuts on the this particular real axis, you this PM gives you the voltage standing wave ratio, and similarly, this particular P small m will give you the inverse of the VSWR. So when it cuts on the negative real axis, it will give you the 1 by S value. So fairly straightforward. Let's take an example. For example, if we had ZL equal to 1.7 plus J 0.6 over here. So this particular point over here that we calculated in the previous slide, we mark the point P. We find that the this particular circle has a radius of gamma equal to 1 by 3, and the reflection coefficient as 28 degree. So we extended this line and we found out that this particular line is 28 degree. And at PM, this R will become equal to S. That is, we this PM will cut this real axis over here, and over here we see that R is equal to 2, which is equal to the standing wave ratio, and hence our VSWR is equal to 2. So yeah, so if once you have the load impedance point mark, you can easily calculate the reflection coefficient, magnitude and its phase, and then the voltage standing wave ratio, just by simply plotting on the spread chart. And for all this, no equations were involved. So in summary, we note the following points: that all gamma circles are centered at the origin. So if you look closely, all these gamma circles are centered at the origin, and this radii uniformly varies from 0 to 1, and anything greater than 1 is not under consideration. The angle measured from the positive real axis of the line drawn from the origin through the point representing the ZL equals gamma. Okay, so this second point means that if you take any particular point, for example, if you take a point over here, and if you draw this line over here, and you calculate this particular angle, this will give you the phase of the reflection coefficient. And if you and using this particular point, if you draw this circle, the radius of this radius will give you the magnitude of the reflection coefficient. So this magnitude will give you the reflection coefficient, this angle will give you the phase, and once you take if you and when this particular circle cuts the real axis on these 2 points, and if you and uh, where this particular circle cuts on the positive side, will for example, if you and then you plus if you look at the R circle passing through it, you'll find out this might be equal to R equal to something 3 or 4, and that will give that R will give you the voltage standing wave ratio. Okay, so maybe we'll pause over here and let you like see what we have discussed till now. So we started at 3:30 and it's 5. So I believe uh, maybe we'll see a couple of more slides and keep the examples for the next class. I don't want to overshoot the time. I've only asked for 3 to 5 of the time as your commitment. So maybe I'll not destroy any plans that you might have. Okay. Um, okay, maybe we can. Okay, this will take time, right? So maybe we'll end the class today over here, and then start do a quick revision in the next class and start with solving problems and other important things from Smith chart in the next class. So it's already about to be 5. So maybe if you have any questions still whatever from whatever you have covered till now, maybe we can take that and the rest of the material will cover in the next class. Maybe and also for the recommendation, you can go through the text from David K. Chang. All this thing that we covered today is already there. Most of the text I've already kept it in the slides. You can, but if you want to go through the textbook, it will be very great. It will be good. So, any questions that you might have till now? Otherwise, we'll stop here for today. So, I hope not much material was left. Hardly markings. Okay. So we had okay. So we only had some examples to do, but maybe it is showing me. Okay, okay, I'm back, I believe. So I don't want to overwhelm everyone. So we'll do the examples in the next class. So yeah, for today's recap, we covered everything that was left in the terminated lossless transmission line special cases. We started with the Smith chart, and in the next class we'll uh, look at some examples from Smith chart and start with transmission line impedance matching. So if we don't have any questions, maybe we can close here for today. Uh, Thanks everyone for joining. I'll probably stop the recording now.